Hi, my dear students. I welcome you all on the lecture series on abstract major theory with course code MMTE 305 and course code MTH 701. This lecture series is for both MA MSc third semester and integrated BSc MSc seventh semester. Okay, so in this lecture we will first discuss the bounded variation functions. Bounded variation functions. Bounded variation functions. Bounded variation function. Okay, let f be a function from closed and bounded interval. Let's define this. Let's have a function f. Let f be a function from closed interval a b to r. It's a real valued function. Okay, and let's take the partition and let p be equal to x naught x1 up to xn, which is equal to b. This xn is equal to b. Okay. Let p equal to the set a equal to x naught x1 up to xn. Xn is equal to b. With the partition of it's a partition of closed interval a b. Be a partition be a partition of a closed interval a b. Okay. Now with respect to this partition, we define the following sum. This is a positive sum, and this sum is called the variation of f with respect to the partition p. So let's define this sum. So define the variation of f. Define that sum is called the variation of f. Define the variation of f with respect to this. So one thing you note that every variation depends on a particular partition. Okay, so define the variation f with respect to partition p. Okay, with respect to p is a given partition, by define this that variation is denoted by this notation v f p. It's called the variation of f with respect to the partition p, and that is equal to summation I runs from 1 to n mod of, it's a non-negative number, mod of f of xi minus f of xi minus 1. So that sum, that positive sum, is called the variation of f with respect to the partition p, because these xi's, they are the points of this partition p. So this sum is actually depends on the partition p. If you vary the partition, we will get the different variations, or we can say we will get the different positive sums. Now next we define the total variation. Okay, and the total variation and the total variation of f over ab, obviously because it's a function from closing interval ab to r on ab is given by or is defined by, can say, or is defined by, that's a notation for total variation t tv of f. Okay, tv of f, it's a total variation of f. It's now look at this. If you vary those partitions, we will get the different variations. So we have actually collection of variations, or you can say the set of variations. That set is obviously the set of non-negative real numbers, because every variation is a non-negative real number. And now we try to find the supremum of that set. That supremum may be infinite or finite, but can define that supremum here. tvf here we can define as an extended real number, because it may be infinite, but in case this total variation is finite, then those functions are some special functions. We name those functions very soon. So let's define that. That's actually the supremum of this v f p. What's p? This p belongs to the partition of the interval a b. Okay, so this supremum depends on the partition. Actually, we vary the partitions, we get the different variations, and then we choose the supremum among those variations. That's called the total variation of f. That's called the total variation of f. And if we choose any subinterval of this closed interval a b, then what will be the variation? If CD is subset of AB, then there was a total variation of f over this interval. Now I will fix here. I will use this notation for this. It depends on, now I want to find the total variation of f over this interval. It's again the supremum of variations of f, but over this interval CD. Okay, that means we have to restrict our function f to this closed interval CD. In other words, we can say that we had to choose the partition of CD actually, where this p belongs to the partition of the interval CD. Okay, so we had to choose the partition of closed interval CD, and then we get the different variations of f over the interval CD, and then finally we choose the supremum. That supremum is called the total variation of f over the interval CT, where CD is the subinterval of a b. So now I will give some examples how to find the variation, then total variation. So suppose let's take this function. Let f be a function from closed interval 0 1 to r, defined by f of x equals to x square. Now let's choose the partition. Let's choose any partition. Let's choose this partition. Say 1. The next point, say I choose 1 by 4 equidistant, then 3 by 4, then 1. Let's choose this part. Sorry, it says 0. It says 0. Okay, the first point is 0. This is 0 here. 0, 1 by 4, 3 by 4, and 1. let this be be a partition be one of the partition of this interval be a partition of closed interval 0 1. Let us try to find the variation of f this function with respect to this partition. So what will be that variation? Let's check that variation. Then variation of f with respect to this partition, that's obviously it's the summation. It's first mod of f of x1 minus f of x naught. So here we have 4 points only. Okay, this is the mod here. Plus mod of f of x2 minus f of x1 plus mod of f of x3 minus f of x2. We have only 4 points, x0, x1, x2 and x3. That's the variation of f with respect to this partition P. Here x0 is the first point of this partition set, that's 0. X1 is the second point, that's 1 by 4. X2 is the third point, that's 3 by 4. And x3 is the last point, that's 1. Or you can see it here. What are those points? These are the points. X0 is 0. X1 is 1 by 4. X1 is 3 by 4. X3 is 1. Okay. So these are the partition points, and that's equal to mod of f of x1 means f of 1 by 4. F of x0 means f of 0 because x0 is 0 plus f of x2 means f of 3 by 4 minus f of x1 means f of 1 by 2 plus f of x3 means f of 3 by f of 1 minus f of x2 means f of 3 by 4. Okay, that's equal to what's f of 1 by 4 means mod of 1 by 4 whole square because f of x is x square minus f of 0 0 square plus mod of f of 3 by 4, it's 3 by 4 whole square minus f of 1 by 2 is 1 by 2 whole square plus mod of f of 1 is 1 square minus 3 by 4 whole square. And that's equal to mod of 1 by 4 whole square means it's 1 by 16 minus 0 plus the next is 1 by 2 whole square. I think let's see this previous page. Okay. This is here 3 by 4 whole square minus 1 by 2 whole square, that's equal to 3 by 4 whole square means 9 by 16. So it's 9 by 16 minus f of x1 minus x0 plus f of x2 minus f of x1. Okay, that's minus minus 1 by, I think this is its first point is 0, then 1 by 4, then it's 3 by 4. It's 3 by 4 minus 1 by 4 whole square actually, not, because this is f of x2 minus f of x1. F x1 is 1 by 4. Okay, first is f of x1 minus f of x0. That's its next point is it's 3 by 4 minus 1 by 4 here. Okay, not 1 by 2. 1 by 2 is not the partition point. Okay, so this is here now 1 by 4 whole square, that's 1 by 16 plus the last mod, that's equal to it's 1 minus 3 by 4 whole square, that's 9 by 16, and that's equal to, this is 1 by 16 plus this one, it's 9 minus 1, that's 8 by 16, and it's a positive number, so we can write it, we can remove the mod here, plus so write this one as 16 by 16, it will be 16 minus 9, that's 7 by 16, again it's a positive number, 7 by 16, and that's equal to 8 plus 1 is 9, 9 plus 7 is 16, it's 16 by 16, that's equal to 1. So 1 is the variation of the function with respect to that partition, and we will show that its total variation is also equal to 1. So why? Because this function is actually monotonic increasing. 9 by 16 minus 1 by 16, mod of 9 by 16 minus 1 by 16 is same as 9 by 16 minus 1 by 16, because it's a positive number. 9 by 16 is greater than 1 by 16, and same is the here, and same is the first difference, which is equal to 1 by 4 whole square minus 0, which is obviously a positive number, so we can remove the mod here. So let's show that, let's prove that the total variation is also equal to 1. Okay, so for this we have to choose any partition, then we have to take the supremum. So let's choose any partition. Let function is same, f of x equal to x square. Let p be equal to a equal to x0, x1, xn, which is equal to b any partition, b any partition of the closed interval 0, 1. Okay, then what will be the variation? Then variation of f with respect to this partition is equal to the summation I runs from 1 to n, its mod of f of xi, xi minus f of xi minus 1. And if you want to expand this sum, as you have seen in the example, it's equal to mod of f of x1 minus f of x0 plus next term is f of x2 minus f of x1, and continue this sum up to n times, and the nth term of the sum is f of xn minus f of xn minus 1. Okay, so now look at this this difference, since the function is monotonic increase, or you can say it's f of x1 is x1 square minus x0 square, it's x2 square minus x1 square. Now here x1 is greater than x0, so that means x1 square is greater than x0 square. Okay, greater than x0 square, so that means we can remove this mod, because it's a positive number as function is monotonic increasing. x0 is less than x1 is less than x2, so on and so forth. So all the numbers under mod, they are all positive numbers, actually they are all positive numbers, so therefore mod of the positive number, which is same as the number, so that means we can remove this mod. It's same as f of x1 minus f of x0, because it's a positive number, plus this one, it's equal to f of x2 minus f of x1 plus the last one is f of xn minus f of xn minus 1. Now look at this difference. Now this f of x1, this is plus f of x1, this is minus f of x1, this will go, this f of x2 will be go with the next term, because next term will be f of x3 minus f of x2. So there is minus f of x2, and here it's a plus f of x2, and these two terms will go. And you will see each term will go, but there remain only two terms, the second term of the first difference and the first term of the last difference. So that means in this sum we have only two terms, minus f of x0 and plus f of x1, and rest of the term will cancel out. Okay, so this is equal to minus f of x0 plus f of xn, and that's equal to what's f of f, it's equal to f of xn minus f of x0, but the function is the square function, it's equal to xn square minus x0 square. What's x and x in the last point of the partition point? That's 1 square minus x0 is the first point, which is 0, because f is a function from closed interval 0 1 to r, which is equal to 1. So the variation is always equal to 1. So thus we have for any variation v, so this implies variation of f with respect to any partition p is equal to 1 for every partition p of the interval a b. For any partition p belongs to the partition of the interval a b. If you take the supremum, what is the supremum? Supremum with respect to the partitions, okay, of the closed interval 0 1, which is also of vfp. If you want to find the supremum of these variations, it's also equal to 1. But what is the supremum? It's actually the total variation. So that means total variation of f. Okay, total variation of f. Total variation of f. Total variation of f is equal to 1. So total variation of this function f of x equal to x square on the closed interval 0 1 is equal to 1. So for some function it may be infinite. We will give an example where this total variation is infinite, it's not finite. Now next we define the bounded variation function. What's the bounded variation function? That's the definition. A function f from the closed interval ab to r is said to be of bounded variation, is said to be of bounded variation if the total variation over the interval ab of the function f is finite, or you can say the supremum of the variations. If we vary the partitions, we will get the different variations, and if we find it a supremum, that supremum should be equal to finite. This should be finite. So in the last example we have seen that the total variation of the function f of x equal to x square on the closed interval 0 1 is finite, because that number that's equal to 1. So therefore that function is of bounded variation. So example is this. This is the example. F of x equal to x square, where x belongs to the closed interval 0 1, is is of bounded variation, is of bounded variation, as its total variation dv of f over the interval 0 1 is 1, which is finite, and this function is actually monotonic increasing. F is actually monotonic increasing. Next, we show that any function which is monotonic increasing is a bounded variation, and the value of the function is equal to the f of the end point minus f of the initial point, f of 1 minus f of 0 here, because here the total variation is 1, which is equal to f of 1 minus f of 0, 1 square minus 0 square, that's equal to 1. So we will show that in general, if f is an increasing function over the closed interval a b, then its total variation is f of b minus f of a. Like here, it's f of 1 minus f of 0, which is equal to 1. So that's the next theorem, or you can see it's also an example of bounded variation function, or you can write it in the form of theorem. Let f from a b to r be an increasing function, be an increasing function, then its total variation t v f over this interval, this is a fixed interval here, is finite. It's equal to, in fact, it's equal to f of b minus f of a, and that's equal to finite, and hence f is a bounded variation. So every monotonic increasing function is the bounded variation. That's an example, because its total variation is equal to fb minus fa. Fb is finite number, fa is finite number, the difference is finite. It's always a finite number. Okay, proof. So let's take any partition. We try to find its variation with respect to any partition, and then we find take the supremum of variations. Let's take this partition. This be any partition. This a equal to x naught x1 xn equal to b any partition of the closed interval ab. Then obviously this x naught, this a is equal to x naught, is less than x1, which is less than x2, less than xn, which is equal to b. Now the function is monotonic increasing, so this implies f of a, which is equal to f of x naught. Now since x naught is less than x1, so f of x naught is less or equal to f of x1, because it's monotonic increasing. X1 is less than x2, so f of x1 will be less or equal to f of x2, so on and so forth. It's less or equal to f of xn, but f of xn is same as f of b, because xn is equal to b. Now name it star. Okay, now we find the variation of f with respect to this partition. Okay, let's find the variation. Now variation of f with respect to this partition p, which is equal to, by definition, it is summation. First you always apply the definition, then you try to expand this sum. Mod of f of xi minus f of xi minus 1, okay, which is equal to mod of f of x1 minus f of x naught plus mod of f of x2 minus f of x1. Now if you want to add one more term here, mod of f of x3 minus f of x2, f of x2 plus the nth mod plus mod of f of xn minus f of xn minus 1. Okay, that's this this expansion of that sum, finite sum. Now this x1 is x naught is less, this f of x1 it's greater or equal to f of x naught. Here you can see this at the previous page you can see it, or you can say star f of x1 is greater or equal to f of x naught, f of x2 is greater or equal to, so the difference is f of x1 minus f of x naught is greater or equal to 0. That means mod of the difference is the same. Mod of the difference f of x1 minus f of x naught is same as f of x1 minus f of x naught, and the same is true for the remaining mod is the rest of the mod is okay. It's equal to, we can remove this mod because it's a non-negative number. It's f of x1 minus f of x naught plus f of x2 minus f of x1 plus f of x3 minus f of x2, then plus then you continue this sum, the last nth term is equal to f of xn minus f of xn minus 1. The term before this one is f of xn minus 1 minus f of xn minus 2. So that f of xn minus, that's minus that f of xn minus 1 will it's here f of xn minus 1, sorry, f of xn minus 1, okay, the last one, f of xn minus 1. So this is minus f of x1, but the term which is before this one, that term is equal to f of xn minus 1 minus f of xn minus 2. That plus f of xn minus 1 will go with this minus f of xn minus 1. So here you will see that all the terms will cancel out and there remain only two terms. One is the minus f of x naught and second is the plus f of xn. Because this f of x1 will go with this minus f of x1 and this f of x2 will go with this minus f of x2 and so on and so forth. All the terms will vanish here except the term, this the second term of the first difference and the first term of the last difference. This term will remain there. Okay, so this is equal to f of xn minus f of x naught. But what's xn? It's equal to b. It's f of b minus f of a. So that means variation of the function v over any partition is always equal to f of b minus f of a, because it's the variation actually. So thus you can see this thus variation of f p is equal to f of b minus f of a for every partition p. P belongs to the partition of p of ab means the set of all partitions of ab, okay, collection of all partitions. So p belongs to p of ab means p is any partition of ab. Let us take the supremum now. It's here supremum of this, where supremum runs over the partitions. Is always equal to, because it's constant. This difference does not depend on the partition, because it's always the difference of endpoints, and that endpoints will never vary. If you take any partition, you have to choose those endpoints actually. They will never change. So that's why this variation is independent of the partition. So it's actually the constant now with respect to the partition. So if you choose the supremum over the partitions, supremum of the variation with respect to the partition, it will be the same, f of b minus f of p. Okay, so or you can say the set of the variation is the singleton set. It contains only one point, because if you vary the variation, you will again get the same number, f of b minus f of p. So that means that set of variations, if you vary the partitions, the set of variations will be the singleton set, and its supremum will be the number itself, the element of the set itself, which is equal to f of b minus f of a. So that means, but this one, it's not total variation, because the supremum is the total variation of f over the interval a b. Understood? That's understood. It's equal to f of b minus f of a, which is finite. So one thing you should note that variation is always finite. Okay, it's always finite because it is some real number. But when you want to find the supremum, that may not be finite in general. Like I can think like this: every natural number is finite. If you choose any natural, suppose you choose 5, it's a finite number. You choose 6, it's a finite number. Every natural number is a finite number. But if you want to find the supremum of set of natural numbers, that's not that's not finite thing. That's an infinite, because the supremum of the set of natural numbers does not exist as a real number. So same thing is here. The variation is always a real number. It's always a finite number. But the supremum of the variation is, because it is a set of the numbers, it has a supremum. That supremum may be infinite or it may be finite. In that case, it is always finite, because here this variation, the variation is independent of the partition. It's not varying with respect to the partition. You will get always this number, this difference. So that this is so we can this is finite here. This is always finite here. If you write this variation of f over p is equal to f of b minus f of p, which is finite, then you take the supremum. Then you write the supremum was also finite. You cannot write like that. You first write this. It's the variation is f of b. Then you apply the supremum. It's again equal to f of b minus. Now you write it's less than infinity. So first, without applying the supremum, you don't write here it's finite, and then you write the supremum is always finite, which is not true. Okay, first you apply the supremum, you will see what number will come out, whether this number is finite or infinite. If it is finite, write it's less than infinity. If it is infinite, then the function is not a bounded variation. So therefore this f is a bounded variation. Therefore this f, which is a monotonic increasing, f is of bounded variation. Okay, this function is a bounded variation function. So next, as an exercise, which is monotonic decreasing. Okay, exercise. Let f from AB to R be a decreasing function, be a decreasing function, then the total variation of f, it's equal to, it's not f of b minus f of a for decreasing, it's f of a minus f of b, and that's finite number. And then you show that, okay, this is an exercise. Then show that this, and hence f is a bounded variation, and hence f is of bounded variation function. Bounded variation function. That's the exercise. Next, we will show that every Lipschitz function is a bounded variation. First, we define the Lipschitz function definition. First, we define Lipschitz function. A function f from AB to R is said to be Lipschitz. Is said to be Lipschitz function. Is said to be Lipschitz function on this interval AB. Okay, Lipschitz function on closed interval AB if there exists a constant C such that if there is a constant C such that mod of f of u minus f of v is less than C times mod of u minus v for all u comma v belongs to the interval a b. And there may exist more than one C's, but there always is a constant C. This constant C, suppose there is one with 1 times u minus v, then 2 will also do the same job. Mod of fu minus f of v will also be less than 2 times mod of u minus v. 3 will do the same job, 4 will do the same job, but we are interested in the minimum, or you can say the infimum of those C's satisfying this inequality. That infimum is called the Lipschitz constant. So we are not interested here for the Lipschitz constant. This is kind of it's the Lipschitz function is the function for which there exists a constant C with this property f of u mod of f of u minus f of v is less than C times mod of u minus v. So next we have a theorem. Which is every Lipschitz function is of bounded variation. Every Lipschitz function is of bounded variation. Proof. So let f from AB to R be a Lipschitz function. Be a Lipschitz function. Be a Lipschitz function. So there is a and let C be a constant. C be a constant. Let C be a constant. Let C be a constant. Constant such that f of u minus f of v, its mod is less than C times mod of u minus v for all uv belongs to the interval a b. Now we show that f is of bounded variations. For this we have to choose any partition that we want. Then we will find the variation, and then we will take the supremum. That supremum should be finite. So let's take any partition. Let p, which is equal to a set x0, x1, xn, which is the last point, be any partition, be any partition of closed interval AB. Now Now we want to find the variation with respect to this partition, variation of f with respect to the partition P, that's equal to summation I runs from 1 to n mod of f of xi minus f of xi minus 1. Now let's expand this sum first, which is equal to, this is the variation. This implies variation of f with respect to the partition P, which is equal to, after expanding we will get mod of, it's equal to mod of f of x1 minus f of x naught plus f of x2 minus f of x1 plus f of x3 minus f of x2 plus the last one, which is equal to f of xn minus f of xn minus 1. Okay, now this one, f of x naught minus f of x1, it's less or equal to c times x naught minus, because f of mod of f of u minus f of v is less or equal to c times mod of u minus v for all u v belongs to the interval. These x naught, x1, x2, so on up to x, and they are all in the interval u a b. So this inequality hold here, which is less or equal to c times mod of x1 minus x naught. It's f of x1, it's here x1, okay, mod of f of x1 minus f of x naught, which is less or equal to c times mod of x1 minus x naught, plus this one, this is c times, c is a constant, mod of x2 minus x1 plus this one, c times mod of x3 minus x2 plus c times mod of xn minus xn minus 1. Now they are all non-negative numbers because x1 is always greater than x naught, so it's equal to, c is the common factor, we can pull out this c from that sum. It will be equal to now x1 minus x naught, because it is a non-negative number, its mod is the number itself, plus this one is also non-negative because x2 is greater than x1, so it's x2 minus x1 plus this one, it's x3 minus x2 plus last one is xn minus 1. Okay, now look at this, x1 plus x1 minus x1, then plus x2 minus x2, and so on and so forth. Again we remain only two terms here, that's minus x naught and plus x1. So this sum is equal to, which implies this variation, it's actually the variation of f over p, it's less or equal to c times it will be here now xn minus x naught, and that's equal to c times b minus c. So this variation, you can see this variation is less or equal to a number which is independent of the partition actually, because we have the endpoints here. Endpoints does not depend on any partition, because they are always the members of they are always the first and the last point of any partition. So you can see this this implies the supremum is always less or equal to, because every variation is less or equal to this. So you can say this is the upper bound of the set of the variations. So that means supremum will be the less or equal to this upper bound, because supremum is the least upper bound of the variations. It's the supremum of v of fp, where p belongs to the partition of AB is again less or equal to c times b minus a, but this supremum, it's actually the total variation. Total variation of f is less or equal to c times b minus a, which is a finite number. So this implies f is of boundary variation function, f is of f is of a bounded variation function. So this shows that every Lipschitz function is of a bounded variation. Now next we will give an example of a function which is continuous but not of bounded variation. That's an example. It's on L-prints. You can see also it on L-prints. Example. Okay. Define a function. If you want page number, it's not an L-print. Sorry. So one thing that I don't mention the book for this chapter, this bounded variation, it's H.L. Royden. Okay, so it's on H.L. Royden. Okay, H.L. Royden, page number 117. Function is of bounded variations. You can see the function of bounded variation on H.L. Royden, page number 117. This example. Let's define this function. Define a function. Define a function f from closed interval 0, 1 to r. Define a function f from closed interval 0, 1 to r by f of x is equal to x times cos of pi by 2x, x times cos of pi divided by 2x when x is not equal to 0, or you can say 0 less than x, less or equal to 1, and its value is 0 if x is equal to 0. Then this f is continuous at every point, also at 0, because its value at 0 is 0 and the limit is also 0. You can easily verify this. So you have to check the continuity only at 0. For other points it's obviously continuous because it's x times cos of pi by 2x for x not equal to 0. So it's really continuous for those points. So you need to check the limit only at 0, that's 0, and the value of the function at 0 is also 0, therefore it's continuous. So then f is continuous, then f is it's continuous. We show that f is not of bounded variation. Okay, we show that this function is not of bounded variation. For this we will try to find the sequence of the partitions, and we will show that the supremum over that sequence of partitions of this closed interval 0, 1, the supremum is not a finite number, it is infinite. Okay, let's choose that partition. For every natural number n, define a partition Pn. For every natural number n, define a partition Pn which is equal to 0. First point is the 0 obviously, and the second point of this partition is 1 by 2n, and the third point of the partition is 1 by 2n minus 1, 1 by 2n minus 1, and the last point is then we have here you continue this partition, then we have here 1 by 3, then 1 by 2, then finally we have 1, the end point of the interval. So choose say for n equal to 1 we have 0, 1 by 2, 1. Then for n equal to 1 the partition is say for example, what's P1? If you want to find P1, P1 is n is equal to 1. So for n equal to 1, we have 0, 1 by 2 into 1, that's 1 by 2, then 1 by 2 into 1 minus, it's 1. So it's 0, 1 by 2 and 1, because last point is 1, so you have to stop this here. So it's 0, 1 by 2, 1. Similarly, if you want to find P2, what is P2? So P2 means n is equal to 2. So it's 0, 1 by 4. Then you can see it's 1 by 3, then 1 by 2, then 1. And you continue this process. This is the sequence of partitions over the interval. They are all the partitions over the interval 0, 1. Okay. Now we try to find the variation with respect to those partitions. Okay, we try to find those variations. Now let's find the variation. Now what's the variation of f with respect to this partition Pn? Which is equal to, by definition, it's equal to summation, or you can say directly, or you can write summation. Obviously, it's summation I runs from 1 to n mod of f of xi minus f of xi minus 1, and that's equal to, if you want to expand this sum, it's mod of f of x1 minus f of x0 plus mod of f of x2 minus f of x1 plus then it's mod of, say, f of x3 minus f of x2 plus you continue this process and times it will be, last one is will be f of xn minus f of xn minus 1. Now what is this? Because we have a fixed partition here for each n, so f of x1 is here, the second point of the partition, that's equal to mod of f of 1 by 2n, okay, minus first point is obviously 0, it's f of 0, plus the third point, which is equal to f of 1 by 2n minus 1 minus f of 1 by 2n, okay, plus you can say it's equal to mod of f of 1 by it's 2n, then we have 2n plus 1, f of 1 by, not 2n plus 1, it's 1 by 2n minus 3, sorry, 1 by 2n minus 3 minus f of, sorry, it's 2n minus 2 here, not 2n minus 3, 2n minus 2, and into f of 1 by 2n minus 1 plus you will see the last one, it's f of 2, f of 1 by 2 minus, or you can see last but one difference, that's equal to f of 1 by 3 minus f of 1 by 2, then last one is mod of f of 1 by 2 minus f of 1. That's this variation. Okay, so let's look this, what's f of 1 by 2n, which is equal to for x not equal to its values, x times x is here 1 by 2n times cos of x by what's the function, let me see the function first. What's the function here? It's x pi by 2x, okay, pi by 2x, x times pi by 2x, x times pi by 2, x is 1 by 2n, x cos of x, x times cos of pi by 2x is pi by 2x, let me see, okay, unit, it's pi by 2x, okay, it's pi by 2x, sorry, it's here pi by 2x, pi divided by 2x, x is here 1 by 2n, minus f of 0 is 0, that's the first term, plus the second term. What's the second term now? it's 1 by 2n minus 1 obviously into cos of pi divided by twice x, twice into x is 1 by 2n minus 1 minus this 1 by 2n into cos of pi divided by 2 into 1 by twice x, x is here 1 by 2n. Then you can take the mod and now plus the next term is plus you continue this process. Now we have f of 1 by 3, f of 1 by 3 is 1 by 3 into cos of pi divided by 2 into 1 by 3 minus 1 by 2 into, because it's f of 1 by 3 minus f of 1 by 2, which is equal to cos of 1 by 2 into cos of pi divided by twice x, x is here 1 by 2, plus the last one is f of 1 by 2 minus f of 1, which is equal to 1 by 2 times cos of pi divided by 2 into 1 by 2 minus f of 1, which is equal to 1 into cos of pi by twice x, x is here 1. So let's try to find out this sum. This 2 and 2 will go, so it will be cos of pi n only. Cos of pi n is equal to the value of cos of n pi, value of cos of n pi. What's the value? Cos of n pi 2 and 2 and 2 will go. Cos of n pi is minus 1 power n, so it will be minus 1 by 2n times minus 1 power n minus 0. Then look at this. It's actually it will be 2n minus 1 times. So let me simplify it again. So then we'll see. This is equal to 1 by 2n into cos of n pi minus f of 0 is 0, okay, mod, plus 1 by 2n minus 1 into cos of, you can see this is equal to 2n minus 1 into pi by 2 minus this value, obviously it's 1 by 2n into cos of n pi, plus the next difference is 1 by 2n minus 3, obviously okay, it's 2n minus this, then 2n minus 1 minus 2n, then 2n minus 3, then 2n minus 2, it will be 2n minus 2, then 1 by 2n minus 2 into cos of 2n minus 2 times pi by 2, okay, minus this one here, 2n minus 1 into cos of 2n minus 1 times pi by 2 mod, plus you continue this process, plus this is 1 by 3 times cos of 3 times pi by 2 minus 1 by 2 times cos of twice pi by 2, that's cos of pi, just pi, cos of pi, plus the last one is 2 minus x1, so f of 1 by 3, f of 1 by 2 minus f of 1 by 3, then it's f of 1 by 3 minus f of 1 by 2 plus then f of 1 by 2, okay, f of 1 by 2 is 1 by 2 into cos of pi minus f of 1 is the 1 into cos of pi by 2, cos of pi by 2. That's the last one. If you want to look at again this at previous page, you want to see the previous page again here. The last one, this is 1 by 2 cos of pi minus cos of pi by 2. Okay. Okay, that's okay. This is it. Now we want to see this sum. We want to see this sum. Cos of n pi is minus 1 power n, but it is under mod, so it will be always positive. It will be always minus 1 power n is either minus 1 or plus 1, but under mod it is under mod. It will be always plus 1. So the value of this one, first term, if you want to find the value of the first term, this one, it's 1 by 2 power n. Now this one, it's odd multiple of pi by 2. Cos of odd multiple of pi by 2 is 0, so it's 1 by 2 power 2 n minus 1 into 0, that is 0, and minus this again cos of n pi, it's again minus 1 power n. It's either values its values are either minus 1 or plus 1, but under mod it's always plus sign, so it's again 1 by 2 power n. So first term is equal to 1 by 2 power n, second term is also equal to 1 by 2 power n. Now the third term, this is here 2 and 2 will go. It's 2 times n minus 1, 2 and 2. So it's n minus 1 cos of n minus 1 times pi. That's minus 1 power n minus 1, which is again plus 1 or minus 1. So it's always plus 1 because it is under mod, but not plus 1. Here you have to check the another difference. This is the odd multiple of pi, but its value is 0. So it's 0. It's 1 by 2 n minus 2 into minus 1 power n minus 1 and minus 0. So that will go because it's 0. It's just 1 by 2 n minus 1 into minus 1 power n minus 1, which is equal to 1 by 2 n minus 2, because minus 1 power n minus 1 is always equal to 0 when you are taking the mod. It's always plus 1. So it's 1 by 2 n minus 2, and the next term you will see that's again 1 by 2 n minus 2. Like here, the first term is 1 by 2 n, and the second term is also 1 by 2 n. Then third term is 1 by 2 n minus 2, and you can see the fourth term, it's again 1 by 2 n minus 2. Now you check the last two terms, and they should be the same. Okay. So cos of 3 times pi by 2, cos of odd multiple of pi by 2, that's equal to minus 1. Okay, it's minus 1. 1 by 3 into minus 1. Now this one, cos of pi, sorry, it's cos of odd multiple of pi by, it's equal to 0. This is minus, okay, this is minus here, it's just minus. Cos of pi is minus 1, so it's minus 1 by 2 into minus 1, that's plus 1 by 2. It's only plus 1 by 2, it's plus 1 by 2. And this one, this is 1 by 2 into cos of pi is minus 1, it's minus 1 by 2 minus cos of pi by 2, which is equal to 0. So minus 1 by 2 minus 0, this is minus 1 by 2, and it's under mod, it will be plus 1 by 2. So last two terms are 1 by 2 plus 1 by 2. So you can see this sum is equal to, 1 by 2n plus 1 by 2n plus 1 by 2n minus 2 plus 1 by 2n minus 2, only even, okay, plus last two terms, it's 1 by 2 plus 1 by 2, and that's equal to, it's 2 by 2, and that's equal to 1 by n, and this will be equal to 1 by n minus 1 plus 1 last. So that means it's equal to actually 1 plus 1 by 2 plus 1 plus 1 by n. That's a variation. Okay, that's variation. So therefore the variation with respect to the partition Pn is equal. So that means we have this variation of f with respect to the partition Pn, it's equal to 1 plus 1 by 2 plus so on. And this sum is not a bounded sum. If n is varying, okay, it's not some, it's not a finite sum. It's here plus 1 by, last term is plus 1 by n. So if you want to find the supremum, if you vary the values of n, you want to find the supremum. That's the supremum of this set of the finite sums is the infinite series, or you can see this, the supremum. This implies the supremum of these variations, where supremum is taken over n greater or equal to 1, means p1, p2, p3, so on and so forth. This is equal to the infinite series 1 by n, and runs from 1 to infinity, which is infinity. So that means because this series is an infinite series, that means the total variation of f is infinite. So this implies f is not of bounded variation, because supremum over these partitions is infinite, therefore supremum over all the partitions will be infinite. So here this is in general, this is not the total variation. Supremum over these particular partitions, it's not the total variation. Total variation is greater or equal to this, but this is infinite and total variation is greater or equal to this variation, this supremum. So that total variation is also, because these are the particular partitions p1, p2, p3, so on and so forth, but we have uncountable number of partitions in general, and there are uncountably many. But the supremum over those countably many partitions, the supremum of the variations over those countably many partitions is infinite. Therefore supremum over all the partitions will be infinite, because that supremum will be greater or equal to this supremum. So that's why this f is not a bounded variation, and this supremum is not finite, it's bound, it is infinite, because for if possible it is finite, then we can choose n so large. Suppose if you assume this supremum is finite, say suppose it is equal to sum c, we choose, and now we know that this sum is if we letting n approaching infinity, this sum is infinite, so we can choose n so large such that the sum 1 plus 1 by 2 plus 1 plus 1 by n is greater than c. The variation with respect to that partition, that n is chosen so large, the variation with respect to that partition is 1 plus 1 by 2 plus 1 plus 1 by n, and that variation is greater than that c. So which implies supremum is also greater than c. But this, you have assumed that the supremum of this partition is a finite number, it is c, which is a contradiction, and you have one element of that set which is equal to the greater than c, because the elements because the supremum, you are taking the supremum of a set. Actually that set depends on the partition Pn. So if you vary the partition Pn, say P1, P2, P3, you will get the different variations, and you have assumed if you assume that this supremum is finite, say C, then the supremum of that set is actually finite, but we know that this series is infinite series. We can choose n so large such that the variation f Pn is greater than that C. So that means you have a member of the set which is greater than the supremum of the set, which is not possible. So that's why this supremum is it's actually simple. It's a trivial. This if we get the elements of the set like this, 1 plus 1 by elements of the set of the variation is like this, 1 plus 1 by 2 plus 1 plus 1 by n. The supremum of that set will be infinite. So that's why this total variation is infinite. Hence f is not of bounded variation. Okay, in the next lecture we'll see that why we study functions of bounded variations actually, because you know that the collection of monotonic increasing functions does not preserve the structure of with respect to scalar multiplication, because we know that the difference of two monotonic increasing functions need not be monotonic increasing, or it is neither monotonic increasing nor monotonic decreasing, the difference of two monotonic increasing functions. So difference of two monotone function is not a monotone function. That's why we study bounded variation function, because this collection of bounded variation, it contains the collection of all monotone functions, because as we have seen that every monotone function is a bounded variation, and we will see that the function is a bounded variation if and only if it is difference of two monotonic increasing functions, and we'll see that this collection is actually it's a vector space actually. If you take the difference of two functions which are a bounded variations, then their difference is again a function of bounded variation, which is not true in the collection of monotone functions. So that's why we study that. We'll explain the next theorem. That theorem is called the Jordanis decomposition theorem, which precisely states that every bounded variation function can be expressed as a difference of two increasing functions. That we'll do in the next lecture. Thank you.